Here we look at the weighted average smoothing filter. The mask shown here on the right is an example of a weighted average smoothing filter mask. The mask shows that the pixels are multiplied by different coefficients, thus giving more importance to some pixels at the expense of others. In this mask, the pixel at the center of the mask is multiplied by a higher value than any other, thus giving this pixel more importance in the calculation of the average. The other pixels are inversely weighted as a function of their distance from the center of the mask. The diagonal coefficients or the diagonal terms are further away from the center than the two horizontal and vertical neighbors, and thus the diagonal neighbors are weighed less than the immediate neighbors of the center pixel. The basic strategy behind weighing the center point the highest and then reducing the value of the coefficients as a function of increasing distance from the origin is simply an attempt to reduce blurring in the smoothing process. Once again, the effect of smoothing as a function of the filter size is illustrated over here. The figures show an original image and the corresponding smoothed images obtained after applying square averaging filters of sizes m equals 3, 5, 9, 15 and 35 respectively. For m equals 3, we notice a general slight blurring throughout the entire image. For m equals 5, again, it is somewhat similar to the figure for m equals 3 with a slight further increase in blurring. For m equals 9, we see considerably more blurring. The result for m equals 15 and 35 are extreme. This type of aggressive blurring generally is used to eliminate small objects from an image. For example, the 3 small squares, 2 of the circles, and most of the noisy rectangular areas have been blended into the background of the image. Also note the presence of these prominent black borders in these last two images corresponding with m equals 15 and m equals 35. Now, this pronounced or prominent black border doesn't exist in the original image. Now, this presence of this prominent black border, especially noticeable when m equals 35, is a result of padding the original image, padding the border of the original image with zeros. Now, note that padding the border of the original image with zeros means that we are actually in fact padding the border of the original image with a black region, because zero intensity implies that the region is pure black. And then we trim off that padded area after filtering. Now, especially in the cases when m is equal to 15 and 35, some of this blackness is blended into the filtered image, but becomes truly objectionable for images which are smoothed with larger filters as compared to images which are smoothed with smaller filters, such as the figure where m is equal to 3 or where m is equal to 5. Here is another example of the working of smoothing averaging filter. Towards the left is an original image of size 528 by 485 pixels from the Hubble Space Telescope by NASA, which was launched in the 1990 and is orbiting the Earth. On the right is the same image filtered with a 15 by 15 averaging mask. As can be noted that after filtering with an averaging mask, the original image is blurred. Now, this blurring is very often very useful when we want to remove small details. So, what this blurring process does is that it tends to blend the small details into the background, leaving behind only the more prominent details or larger objects which are of more interest. We now briefly visit a Gaussian smoothing filter. Over here on the right, a sample or an example 7 by 7 Gaussian filter mask is illustrated. The filter coefficients or weights are samples from a two-dimensional Gaussian function. A sample or an example two-dimensional Gaussian function is also illustrated over here on the left. So the weights or coefficients of a Gaussian mask are basically samples of this two-dimensional Gaussian function. Over here, we can study that the response of a Gaussian smoothing filter depends on the standard deviation of the Gaussian function. If the standard deviation is small, if the sigma is small, there is limited smoothing or less smoothing. If the standard deviation is large, sigma is large, the smoothing is stronger. Finally, we move to nonlinear smoothing filters. Order statistic filters are nonlinear spatial filters whose response is based on ordering or ranking of the pixels contained in the image area encompassed by the filter, and then replacing the value of the center pixel with the value determined by the ranking result. One of the best known filters in this category is the median filter, which, as its name suggests, replaces the value of a pixel by the median of the intensity values in the neighborhood of that pixel. Median filters are quite popular because for certain kinds of random noise, they provide excellent noise reduction capabilities with considerably less blurring than linear smoothing filters of similar size. Although the median filter is by far the most useful order statistic filter in image processing, it is by no means the only one. Another example of an order statistic filter is max filter. Max filter is very useful in finding the brightest points in an image. As the name suggests, it replaces the intensity of the center pixel P with the maximum intensity amongst its neighboring pixels. Likewise, the minimum filtering or minimum filter helps in finding the least bright points in an image. The intensity value of the center pixel P is replaced by the minimum intensity of its neighborhood. The example over here illustrates the usefulness of median filtering in reducing or removing salt and pepper noise from an image. Salt and pepper noise, also called impulse noise, appears as black and white dots superimposed on an image. Now, the figure on the left is the original image. The next figure is the original image that has been degraded with salt and pepper noise. As you can observe, that the salt and pepper noise is a mixture of black and white dots that have been superimposed on the original image from the left. The third image is the output of an averaging smoothing filter, and the fourth image is the output of a median smoothing filter. If you observe the last two figures carefully, you will be able to see that the median filter outperforms the averaging smoothing filter in reducing or in the removal of noise, While the averaging filter also is able to reduce noise up to a certain degree, the median filter definitely outperforms the averaging filter. The example over here again illustrates that while the averaging filter blurs the image, its noise reduction performance is rather poor. Now the figure on the left is a noisy image. The figure in the middle is a 5 by 5 median filtered image, and the figure on the right is a 5 by 5 box filtered image. You should be able to observe that while the box filtered image or the averaging filtered image is an improvement over the noisy image, nevertheless the median filtered image is superior to the averaging filtered image.